let's go and get started. Let me get this loaded up, and let's see, get the lights adjusted. There we go. All right, so sign-in sheet. Go ahead and get that passed around. Okay, so a little bit of housekeeping. I have not yet graded your exams. I'm working on it. I guess the only thing I would say is I wouldn't get too stressed out. No pun intended. I don't, I usually give the exams a once-over to see, if there are any, major problems that need to be addressed, and I didn't really see that. So I've just got to grunt through it. My plan is to get it back to you on Tuesday, so that's sort of the idea. Oh, excuse me. No, that's fine. Just a quick heads up, just a little bit of housekeeping. We're going to have a visitor on Tuesday. Dr. Nichols is going to come. There's just some routine class visitations he's going to be doing, so he's just going to be hanging out in the back. So if you see Dr. Nichols sort of walk in and just sort of sit down, don't, what are you doing here? No, it's routine and whatnot, so he's just going to be coming in. He'll probably just sit in the back and hang out. So everybody okay on that? All right. So I know it's been a while since we've talked about a lot of this, so I thought I'd sort of go back and sort of, I guess, recap a little bit. Before we left, we were talking about beam deflections. We talked about beam deflections, and then we were even in the middle of an example, and then we said, dun, 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 to be continued, because we sort of had to stop and say, all right, we got exam review, we've got an exam, and then now it's time to pick this back up. So we've got to go through beam deflections a little bit, so I want to recap where we left off, get into our example a little bit, and sort of press on with our beam deflection calcs. We've got two methods that we're going to use in this course. One of them is direct integration or double integration to derive the formulas, and then the second method is just going to use the formulas directly through superposition. So to start, I guess I'll start here. Remember, we were looking at beam deflections, and we derived our fundamental diffie-q for beam deflection. That is that the second derivative of deflection is m over EI. One of, excuse me, one of the arguably the most fundamental equations in all of mechanics and in all of engineering, really, the beam deflection equation. The reason why is because you can use this expression to relate loads all the way back to deflection through a relationship between load and shear, between shear and moment, between moment and curvature, between curvature and slope and deflection. You can connect the dots, hip bone connected to the leg bone, all the way from beginning to end. So it's a really fundamental expression that ties everything together. If we're interested in solving for deflections, I mean, theoretically, yes, this is a differential equation, but it's a pretty straightforward one. If we have that the second derivative of deflection is m over EI, just integrate twice. And there you go. Now, when you integrate twice, you're going to get unknown constants of integration. For instance, what's the integral of x squared? It's x cubed over 3 plus c. So we have to solve for that plus c. We have to solve for that constant. And we solve for that using boundary conditions. So our boundary conditions come from the physical restrictions on the beam. So for instance, I'm more concerned with 1, 2, and 3. These 4 are just sort of food for thought for later. But if I have a simple support, and a simple support could either be a hinge or a roller, it really doesn't matter for the purposes of what we're talking about, because we're talking about deflection. And I propose that regardless of whether you're dealing with a hinge or a roller, in that scenario, at that particular point, the deflection equals 0. So we use those boundary conditions to solve for those constants. So that's one particular boundary condition. Another is a fixed support. Okay? At a fixed support, not only is deflection 0, but rotation is 0 as well, or your slope is 0, because you're not only restraining the vertical force, you're restraining the bending as well. That's the difference between a simple support and a fixed support, that you're including that moment reaction. So those are our boundary conditions. The only other thing you've got to look at are units. And in SI, it's pretty simple. I mean, it's all just, 10 to the third or 10 to the sixth. Just make sure you're tracking your prefixes, and it's actually pretty simple. It's more complicated in in US units. When you plug in, I guess, what I would call traditional units for deflection, you're going to get your loads are going to be in kips probably, and your member lengths are going to be in something like feet, but your moments of inertia are going to be in inches to the fourth. Your modulus of elasticity is going to be in KSI. So when you go through and just plug that out, you get a mismatch in units, so you have to throw in a conversion factor. They're pretty easy to derive. They're all just functions of inches, you know. If you look at deflections, you end up having a foot cubed left over, so if you want to convert that into inches cubed, you'd take 12 to the third power. So 12 times 12 is 144, times another 12 is 1728. So whenever you do deflection calcs, you can plug everything in, you know, traditionally that you would normally use, you know, member length of 30 feet, a distributed load of 2 kips per foot, what have you. But all in all, when it's all said and done, you have to multiply your answer by 1728 to do your appropriate conversion. And this is stuff we all talked about previously. I just wanted to sort of run through this again. For rotation, we're not left with a cubic foot, we're left with a square foot. So instead of multiplying by 1728, we multiply by 144. But that'll generate an answer that's in radians. If you want a little bit more of a manageable number in degrees, you've got to multiply by 180 over pi. So here's your deflection unit conversion, and there's your rotation unit conversion. Everybody okay with this? I know it's been a little while since we did this. I thought, what the heck, it's probably worth a couple minutes to recap. All right, everybody good? Now this is where we left off. We were looking at this beam, and we said, all right, let's determine the deflection in this beam. Let's determine an expression for deflection as follows. And then we're going to determine what is the maximum slope in deflection based on those parameters. So this was the beam we were looking at. We had an EI that was constant, so we could factor that out. Made our lives a little easier. So let me pull up the work pad, and let's see what we remember. Excuse me. So the first thing that we did is we said, all right, let's look at the beam. Okay, so here's the beam. We have our x-axis and y-axis. Notice how we've got that drawn. We have a distributed load, W, acting over the entire length of the beam. So my reactions are WL over 2 and WL over 2. Now before we started writing expressions, we said, you know what, let's just treat this like a normal problem. Let's draw the shear diagram, draw the moment diagram. So what's the shear diagram look like? We go up WL over 2, right? We have a distributed load, so we go down linearly, and we go back up. So there's our shear diagram. Calculate the area under that to get the moment diagram, and here's what we got. So this told us that our shear diagram, or our shear function, would be a line, and our moment function would be a parabola. Everybody remember that? And remember, it's that integral relationship. You know, if you take the integral of a line, you're going to get a parabola. It's like, what's the integral of x? It's x squared over 2. So, all right. Now, that's nice, but what we actually need are moment functions. Now, we went ahead and did the shear function for the heck of it just to check our results. We're not going to use this, but we said, what the heck, let's just make sure our math is right. So remember, samurai sword or a lightsaber if you're a sci-fi fan, right through the section. Look either side. It doesn't matter. Okay, we look to the left. Look towards our origin. Made it a little easier. So cut a section. Look this way. We have WL over 2. We have some distributed load. Cut. We've got an unknown shear and an unknown moment. Remember, that's our positive sign convention, so that's the direction we've got to draw it. Collapse that into a point load, W times X. It's a rectangle, so there's the centroid. Sum forces, sum moments. So when I sum forces, I got WL over 2 going up. Going down, I got WX, and I got my shear. Solve for that, and that's what you get. Same thing for the moments. Some moments at the cut. Got WL over 2 times X going like that. This side, I've got WX times X over 2, and I've got bending moment. Solve, and there you go. And the big thing to look at that was your calculus. What is the derivative of that? It's that. Derivative WL over 2 times X, WL over 2. Derivative of W over 2 x squared is W over 2 times 2x, and there we go. Everybody okay with that? Just sort of getting everybody thinking about this again, because I know it's been a while since we've done this. Ultimately, though, I only give a damn about the moment function. So here's our moment function, and we've got to integrate twice. So we integrate once, and that'll give us the slope function. So integral of this, we got WL over 4x squared, that gives us that. W over 6x cubed plus C, remember the unknown constant of integration? I call that C sub 1 because when I integrate again, I end up getting another one, a C sub 2. So that helps me keep track of it. Everybody good? Now the boundary conditions, that's the big one, okay? This is a simply supported beam, okay? So going back a little bit, all right, it's a simply supported beam. So I know that deflection here and deflection here is 0, right? This is the point where x equals 0. This is the point where x equals L. So here's how I get those two coordinate systems, or those two boundary conditions, sorry. At x equals 0, the deflection's 0, and at x equals L, the deflection's 0, okay? Now, that is going to change on the next example because we're going to be using different boundary conditions. Why? Because we're not dealing with a simply supported beam, it's a fixed-ended beam. So just keep that in the back of your head. Everybody good? All right. Now to evaluate these, we plug and chug. So we say, all right, here's EI times Y, which we evaluated right here. Plug in 0 for Y, or 0 for Y, 0 for X, plug and chug. And if you go through that, you get that C2 equals 0. Everybody okay with that? Any questions? All right. Now we can get back to it. Whew. A lot of recap, isn't it? But I thought it was valuable just because it's been so long since we looked at this. Okay. Excuse me. All right. So let's look at boundary condition 2. So we have EI times Y equals WL over 12 x cubed minus W over 24 x to the 4th plus C1x. And then technically there's a plus C2, but we already know what that is. That's 0, so there's no reason to deal with it. All right? Now, here's my deflection function. Here's how this works. I plug in x equals L. I plug in y equals 0, and plug and chug. So, EI times 0 is WL over 12 times L cubed minus W over 24. What did I do there? Pen got away from me. Times L to the 4th plus C1 times L. Everybody okay with that? So I plugged in x equals L, and I plugged in y equals 0. So everywhere there was a y, that turned into 0. Everywhere there was an x, that turned into L. Everybody okay with that? Now, one check to see whether or not you're doing this right is this, okay? Let's grunt this out a little bit. So over here on the left, EI times 0 is 0, right? EI-EIO. Got everybody paying attention. There you go. It's 8 o'clock, but I still got the jokes. All right? Now, this first fraction, I've got WL times L to the 3rd over 12. So that's WL to the 4th over 12, right? Right? How about this one? WL to the 4th over 24. See that? You're adding these terms together, and notice how stuff that you're adding together contains the same parameters. It's a WL to the 4th minus a WL to the 4th. I mean, the coefficients are different, and it's the same chunk of material being added together. Make sense? It gives you an idea that what you're doing makes sense, that you're following along the right path. Okay? Now, what I can do is think of this in like terms. You know, I have, I mean, we've got WL to the 4th, so I can say I got a pile of junk times a 12th minus a pile of junk times a 24th. So I can factor that out. So what is 1/12 minus 1/24? You all have? No, think about that. This is 1/24, yeah, because this is essentially going to say 1/12 minus 1/24, which is 2 over 24 minus 1 over 24, right? But that's what the Casio's for, right? You're like, it's too early to do fractions. No, that's fine, that's fine. And in all honesty, if you're in doubt, I mean, that's what it's for. So, sound good? All right, so combining these two terms, I can get 0 equals WL to the fourth over 24 plus C1L. So, you know, sometimes it's tempting to go, wait a minute, you had WL to the fourth over 12 minus WL to the fourth over 24. What did you just say? That magically vanished and this became positive? No, it's this. Okay? Does that make sense? So make sure you're following along with that. Okay? So what I can do is solve. So I can say C1L is, you know, subtract on the other side, minus WL to the fourth over 24. So I get C1 is minus what? There you go, WL to the third. 24. That looks like a Y. It's gonna bug me. Can everybody still read that? You all good in the back to read that? Okay. All right. Everybody good? So that was the whole point. We've got our deflection expressions. Here's C1 and here's C2. Everybody good? So if I want, what I can do is this. All right, has everybody got this? Can I go ahead and go to the next panel? Okay. So let's start off with the first one. Let's start off with the slope. So EI times theta, when we derived that, what did we get? I think we got WL to the fourth, or WL over 4, sorry, times x squared, what was it, minus W over 6, x cubed, and then plus what, C1? Is that right? That's a theta, I'm sorry. Yeah, I can see. Here, how about I do this? EI theta, but then of x. So it's a little easier to see. Okay, now does everybody see where I'm getting that? If you go back, I'm going to go back a slide, but if you go back, remember, that's this. You know, the first integral, that's what we got. But now we know what C1 is, right? Which is WL over 4 times x squared minus W over 6 x to the third minus that. Make sense? So I propose to you that theta of x is 1 over EI times the following. That's one of them. And if you want, you can try and, if you're lazy when you use your calculator and you're thinking, well, why don't I factor out the W? You know what I mean? I could factor out the W because each term has a W. Or I could factor out, I don't know, maybe like a 2 on the bottom or something, you know, because I've got 4, 6, and 24. Maybe I can factor out a common fraction to, you know, make my life a little easier on the math. You could do that. But in the end, that's your answer. Does that make sense? So this tells me what the slope of the beam is across the length. And we're going to look at that here in a second to make sure this makes sense. Okay? Now, EIY is what? Let's see. WL over 12 times x cubed minus W over 24 times x to the fourth plus C1x plus C2, right? That's what we originally derived, right? And that just came from right here. Just integrating it out and chugging it out. Sound good? All right. So, plug in our constants. What was C2? 0. What was C1? WL cubed over 24, right? Okay. So, WL, sorry, whoop. That was not right. WL over 12 times x to the third minus W over 24 times x to the fourth plus, or no. C1's minus WL to the third 24 times x. Sound good? So factoring everything out, y of x is, or dividing the EI, 1 over EI times. All right. Does that make sense? So far, so good? Now, let's be clear about what these represent, okay? These represent the deflection and slope of this beam. Let's just use our noggins a little bit, okay? I have a beam that looks something like this. Okay, here's the beam. All right, another thing I'm going to put, this is x, that's y, okay? It's being subjected to a uniformly distributed load, right? Going like this. So, would a fair statement be that when I apply this load, the beam's going to deflect something about like this? Would that be a fair statement? Something about like that? Now, let's break out the calculus knowledge a little bit. Okay, so that's L. Where is maximum deflection going to occur? Say it again. L over 2. You're right. At the center, but at x equals L over 2. Is everybody okay with that? Now, let's break out that calculus knowledge a little bit. What should that equal at L over 2? 0. Okay. We're talking, all right. This is the deflection. That's deflection. But this is the slope. That's theta. Okay. So y max occurs at x equals L over 2, and at x equals L over 2, theta better be 0, right? Does that make sense? Now let's see if that happens. Just a check. So theta at L over 2 is 1 over EI. And what I'm doing is I'm taking this expression and I'm plugging in x equals L over 2. Make sense? All right, so WL over 4, here, let me replace that with a bracket. So we have L over 2 squared minus W over 6 times L over 2 cubed minus WL cubed over 24. Is everybody okay with that? Okay. Now, let's do a little bit of plug and chug. What is L over 2 squared? L squared over 4. Everybody okay with that? Now, if I take L squared over 4 times that, what's that going to be? WL to the cube, or WL to the third over 16. That's a 4. Yeah, so 4 times 4. Everybody okay with that? Fractions. 1 over EI WL to the third over 16. All right? Everybody okay with this? Minus W over 6 times L over 2 to the third. Now let's start off with the L over 2. What's L over 2 to the third? Here we go. L cubed over 8. Now I saw you sort of do it like WL cubed over 8, but there's a 6 there as well. So what do I do? Minus WL to the third over 24. Fair point? So can I factor out the WL to the third? So WL cubed over EI times that. Making you break out the Casios and whatnot. Oh, break out the Casios. Remember, common denominator, 1 over 48. If I do this over 48, that's 2. And if I do this over 48, that's 3. 16 times 3 is 48. It's 0. So this is WL to the third over EI times 0. So wait for it. Right? Does that make sense? Okay. Now, okay, so that's our check to make sure that our equations and whatnot are making sense. Sound good? All right. Let's ask a couple other questions. So maximum deflection occurs at L over 2. Where's the maximum slope occur? Say that again. Say it louder.
At either support.
At either support. So at x equals 0 or at x equals L, we get maximum slopes. But watch what's going to happen. At x equals 0, our slope looks something about like that, right? At x equals L, our slope looks something about like that. So we're going to get the same value, same magnitude, but they'll be opposite signs. There you go. So one will be negative and the other will be positive. All right. Everybody good? So let's carry this out. Has everybody got everything over here? Okay. Oh, getting tangled. All right, so let's look at maximum deflection and slope, which you all are going to need your Casios out for this, so unless you want to do the conversion, that's fine. But now, let's start off with maximum deflection. Maximum deflection occurs at L over 2, okay? Which is 1 over EI, and I'm going to need a bracket. Okay. So let's see. We got WL over 12 times what? X cubed? So that's L over 2 cubed minus W over 24 times L over 2 to the fourth, right? We got minus WL to the third over 24 times L over 2. I do that right? Okay. Now, let's check this out. Let's just look at the variables for now. So WL times L cubed is what? WL to the fourth? right? And this is WL to the fourth. WL cubed times L is WL to the fourth. So that's a check that what we're doing is right. So 1 over EI. So we have WL to the fourth over 12 times 8, yeah, which is 96, minus WL to the fourth over 24 times what? 16, minus, what's that? You're right. Everybody okay with this? So can I factor out a common term? I can factor out the WL to the fourth, right? Okay. So WL to the fourth over EI, whoa, what the heck? Times 1 over 96. All right, I can do better than that. 1 over 96 minus 1 over, what did you say, 24 times 16, 384? Yep. And then minus 1 over 48. Okay. So I'll leave you to do that and tell me if you can get a fraction for that. That's an involved one, I know. It might be too early for that one. That's fine.
Take that 12.
Well, what's that? That. Okay, all right. He got negative 5 over 384. Did anybody else get that? Yeah. Okay. It comes out negative, okay? In fact, it comes out to be negative 5 WL to the fourth over 384 EI. Okay. Does anybody have an idea why the answer came out negative? Well, here, let's keep it simple. It's going down. Yep. Here's our coordinate system. It's deflecting downward, you know? Simple, right? All right. Everybody okay with that? All right. So there's that. Let's do theta max, which it's going to be either at x equals 0 or x equals L. I think it's a whole lot easier plugging in zeros than it is plugging in L's. So I'm going to plug in 0. So theta at 0, which is 1 over EI. I'm lazy, you know. Be lazy when you can be. All right? So that's 1 over EI times WL to the fourth, or WL over 4, sorry, WL over 4, times 0 squared minus W over 6 times 0 to the third minus WL to the third over 24, right? Pretty easy to deal with, right? It's just minus WL to the third over 24 EI. Everybody all right with that? Now, see how it came out negative? Now this is at x equals 0, right? So if I go back, look what's happening. At x equals 0, it sloped down like that. That's a negative slope, right? Now if you want to carry all the fractions out, you can plug in x equals L, and I promise what you're going to get is positive WL third over 24 EI. Now, for some of you that are thinking, God, that's a bunch of letters and alphabet soup, I need some meaning to it. Let's plug in some values, okay? So let's go back to the slide real quick, the PowerPoint slide. So let's determine what the maximum deflection and slope of this beam would be if it was made out of steel, so it's E equals 29,000 KSI. It's a reasonably large beam, and the I is 1,500 inches to the fourth. The beam's 30 foot long, and it's subjected to 2,000 pounds per foot, or 2 kips per foot. So let's see how much it would actually deflect. All right? So I'm going to scroll down a little bit. So for our beam, we have W is 2 kips per foot. L is 30 feet. E, 29,000 KSI. I is 1,500. Sound good? So, let's do Y max. Minus 5 times 2 times 30. And I'm being a little fast and loose with the units. You know what? No, I'll tell you what. Let's write it out. Let's write it out. Kips per foot times 30 feet over 384 times 29,000 KSI, 1,500 inches to the fourth. Does everybody see where I'm getting at? This formula, and just plug it in this data. Now, does anybody see a problem with that? Looks to me like we got a bunch of feet on the top and inches on, and the units on the top are in feet. But we already handled that, didn't we? I thought we derived a nice, pretty unit conversion for us. Remember that? Our unit conversion for deflection was 1728. So I propose what we're going to do is this. Multiply this times 1728. And the reason why is because that's cubic inches per cubic feet. And that'll get everything into an answer that's in inches. Oh, you're right, you're right. No, we're at like mistake number 5, and I'm gonna call that like you know what? I'm gonna call it 4.5 because that's a tiny mistake. So. But I had it right up there, so I don't want to hear it. All right, so anybody got a number for me? Here, I'll erase that since I'm just going to write it out. Putting those Casios to work. I like it. Okay, I guess somebody's got .838. Let's see if anybody seconds him. Seconded. All right, 0.838 inches. You put that much load on a beam that's that long with those properties, it's going to deflect a little over 0.8 inches. About like that. Good. What's that? Well, what's that? That's a pretty sweet deflection for the steel bridge, yeah. Problem is that you can't just use this nice pretty equation because this nice pretty equation is for a simply supported beam. You got an overhanging beam, and it's not a nice constant beam. It changes all over the place. So we got some juniors and seniors that can help you with that, though. So. And we got some software that can help as well. So we'll get there. All right, everybody okay with this? Now, rotation. Minus 2 kips per foot times 30 feet. Can't forget the exponent there. Because some people are going to call me on that. 24 times 29,000 KSI. I mean, just, point out all my faults, why don't you? 1,500 inches to the fourth. Okay. Now, what's our conversion factor? There you go, 144 times 180 over pi. And where are we getting that? We're saying there's 144 square inches in a square foot, and then we're also saying there's 180 degrees in pi radians. So this is also going to come out negative, but now while you're doing that, I have had people ask me, they say, well, hey, can't we just, do this in radians and convert, using our calculator mode? Yeah, I mean, I'm sure that's true, but honestly, I'd rather just plug the numbers in and chug it out, because I have a feeling that it can get a little more confusing when you're doing that, if you're getting the wrong conversion during, like a homework or exam. I mean, you've got this nice, pretty conversion factor, just use it. All right, somebody else. What we got? Somebody else. Anybody got a number for me? It's Wait, what'd you say? Yeah, it is. Oh, I see. You should have said, well, it's not negative 0.428. Okay, I got 0.427. Anybody else get that? Okay, so that's degrees. Something like that, yeah. At that point, I mean, you're talking about a beam rotation to the thousandth of a degree. That's pretty good. So, and you might think, do you ever use angles that are that accurate? And the answer is actually, yeah. There is one particular instance, and I'm sorry for you mechanicals. I relate everything to civil stuff. But in bridge design, when you're designing the bearing pad, which is, it's basically this elastomeric, like rubber type pad that transfers the load from the beam to the foundation. We use this little rubber pad because it translates very nicely. In other words, the bridge gets hotter or colder, and the beams, get long. What happens when the temperature rises? Things heat up. Remember that? So when the bridge gets hotter or colder, it wants to expand and contract. You need a device that allows that rotation, or that translation and that rotation very nicely. And these elastomeric pads that have sort of steel plates in the middle, they work pretty well. But in order to design them, you need dead load rotations, and they get, that accurate. So we do use the, stuff that accurate. Just, food for thought for later days. Okay, does anybody have any questions? Everybody good? Everybody good? All right, we're going to do one more because I want you to have a little bit more experience with this, and I really want you to understand this. So we're going to do one that's a little different. It's going to look like this. Now, a couple things about this one that are a little nicer. Number one, we don't need to do support reactions. We don't need to compute those because I'm going to define the coordinate axis from the other side, which there's nothing against that. As long as you're consistent, you're fine to do that. That's point one. Point two, I left the variables off of this. There's no, a length of L or a load of P. It's just 10 kips and 24 feet. So hopefully the integration and the grunt work goes a little faster, okay? Now, one point I do want to make, okay, before we even start the problem, let's make a few observations, okay? Point one, where is maximum deflection going to occur? Before we even do any math. At B, right? Now, is that deflection going to go up or going to go down? There we go. Okay, we got that figured out. Okay. What is deflection at A going to be? Okay, there we go. Now, let's also do something. I propose that the beam's going to deflect. It's going to look something about like that. You know, forgiving my horrendous art skills. Where is maximum slope going to occur? At B, right? And what is the slope at A going to be? Exactly, it should be 0. So not only will that serve as a check to see whether or not our math is right, but that slope is also going to be, or that slope at A is going to be a boundary condition. Does that make sense? Everybody okay with that? All right. Okay. Where are we? Example 26? I would say, can you believe we've done 66 pages of all this? And people are like, yeah. Yeah, I can. What was that, 10 kips? And this is 24 feet. Okay. This is A, and this is B. Now, we were also given that E was what, 4,000? And I was 8,000. So the idea is this. This beam is probably, instead of being made out of steel, it's probably made out of something like concrete. And the thing about concrete is that in order to get the same stiffness, you just need a bigger beam, okay? So we've got, you know, on our last problem we had E was 29,000, but I was only like 1,500. Well, to get the same stiffness, you need a much larger section. So in general, if you look at a steel beam versus a concrete beam that are supporting the same loads, the concrete beam is much larger because it's just got to be. Concrete isn't as strong, so you need more of it. All right. Now, what I'm going to do for this is I'm going to take my coordinate axes and I'm going to flip them. Okay? In other words, I'm going to say that my origin is right here, but the x-axis goes in the opposite direction. Okay? And you might go, well, can you just do that? Can you just arbitrarily do that? Well, why not? What if I took what if I took the beam and just turned it instead? What if I did this? What if I said, you know what? Let's take this beam and flip it and get this. I mean, let's be honest with each other. Is this beam going to behave any differently than the one above it? No. It's still a cantilevered beam that's 24 foot long, that's with these properties, it's being subjected to a 10 kip load. It doesn't matter. Okay? So I'm essentially going to flip the beam around. Okay? Does that make sense? Everybody okay with that? Okay. All right. So remember, secret weapon of structural engineering, samurai sword or lightsaber, you know, if you happen to be a sci-fi fan. So I'm going to cut a section, and I'm going to look towards the free end, okay? So if I'm looking right here and I look towards the free end, here's what I got. I got this. I got that. 10 kips. Now, I've got an unknown shear and an unknown moment, right? How long is that segment? It's X. There we go. All right. So if I sum moments at the cut, I say everything spinning one way has to equal everything spinning the other way. So I'm at the cut. Do I get any moment from shear? If I'm summing moments right there, it'd be V times what? There we go. Getting you all woken up. All right, we've got moment going like this, so that m, or if you want to say m of x, that's fine. And we've also got the 10 kips. 10 kips acting at a moment arm of x. And which side, left or the right? Left, right? Because if I'm at the cut, it's spinning it like that. So what's going to happen is this. I get m plus 10x equals 0, or m is minus, oh, I'm getting ahead of myself there. M is minus 10x. Now, can your moment function be negative? Well, think about it like this. If I take that 10 kips and I put it on that beam, it's going to deflect like what? Is it going to behave like smiley face or frowny face? Frowny face. The whole beam is going to frown, so it's going to experience negative bending, right? Make sense? So it makes sense that this should be negative. Right? Too bad, right? Now, double integration. Actually, you know what? No. Let's not do that yet. Let's do our boundary conditions. Now, how many of them are we going to need? 2. We integrate twice, so we get 2 constants. Now, would you agree? Here, I'm going to erase this because I don't want it to get confusing. Would you agree that our beam's going to deflect something about like that, assuming it's a little more rounded? About the best I can do. All right. What can you tell me about the deflection at A? What can you tell me about the slope at A? All right. Now, what can you tell me about the value of x at A? 24. There you go. Because this is x equals 0. This is x equals 1, x equals 2, x equals 3. This is x equals L, or x equals 24. So here's our boundary conditions. At x equals 24, the slope is 0. And at x equals 24, the deflection is 0. Does that make sense?
Because it's going from the 10 kips.
Yeah. I said yeah, because this is x equals 0 and x goes that way. Make sense? Now let's do some double integration. So, you are excited for the calculus. You haven't quite hit your limit yet. This stuff is just so integral to everything that we do. Gotta love it, right? Now, we do one integral to get the slope function, which is the integral of minus 10x dx. So what's the integral of minus 10x? Well, so we factor out the negative 10, and what's the integral of x? X squared over 2. So if this is x squared over 2 times negative 10, it's minus, but plus C1. There we go. We got that constant. Okay. So we've got EI theta is minus 5x squared plus C1. Can anybody see something we can go ahead and do right now? We can solve for C1 because we can use this. We can use that first boundary condition. Let's just go ahead and do it. So boundary condition 1. So we have EI times the slope of 0 is minus 5 times 24 squared plus C1. So 0 equals C1 minus, what's 24 squared times 5? That's what the calculator's for. So it's, was it 120 times 24, 2880. So that's 2880. And there you go, right? Not too bad, right? All right, your next one. We got to integrate again. But before I do that, everybody got this? Okay. All right, so we got EI times Y. So we got to integrate, was it minus 5x squared? Was it plus 2880 dx? So what do we got? We got minus 5x squared, so minus 5 times what? X cubed over 3, right? So that's minus 5 over 3x to the third plus 2880x plus C2. And now we can deal with C2. So EI times 0 minus 5 over 3 times 24 to the third, right? Plus 2880, bless you, plus C2. So C2 equals 5/3 times 24 to the third. Come on, I can do better than that. Minus 2880 times 24, right? So I take, this, bring it over, so that's plus, take that, bring it over, so it's minus. Did I do that right? Sure everybody's paying attention? All right, so what do we got? C2 equals, that's what you got, negative 46080. That's what you got. So here's our functions. EI theta is minus 5x squared plus 2880. EI y minus 5 over 3x to the third plus 2880x minus that. There's our functions. Simple, right? Everybody okay with that? Now, where does maximum slope and deflection occur? And what is the x-coordinate at B? 0. All right? Everybody see that? Maximum slope and deflection occurs right here, and that's x equals 0. So all I got to do is this. EI theta max is EI times the slope at 0, which is minus 5x squared, minus 5 times 0 squared plus 2880, which is what, 2880? So therefore, theta max is 2880 over EI. So what's E? $4,000. What's I? 8,000, right? So watch this. This is what I'm going to do. 4,000, 8,000, 2880, and then I'm going to do 144, 180 over pi. 0.742. Who seconds that?
Depends on
This matters, man.
civil engineering.
How about this? Since you all have to be particular. I just have it just direct rounding, and I think it went 743, but all right, everybody okay with this? But since somebody has to be particular, no. Well, that washes everything else. That's not a mistake. That's correcting the mistakes. I should go to like 3.6 or something. All right, Y max. Here, how about this? Let's do Y max. All right. So here's EIY, and if I want to find EIY max, I plug in 0, right? So that's, here's our expression right here. So it's minus 5 over 3 times 0, all right, plus 2880 times 0 minus that. So make sense? So that's what? Minus 46,080, because everything else is times 0. So I propose that Y max is minus 46080 over EI. And it's minus because it's deflecting downward. So minus 46080, 4,000 times 8,000, and then our lovely conversion factor, 1728. Or what do we get? Negative 2.488. Anybody else get that? That's what you got? All right. Not quite. Not quite. Nice try. Any questions? This isn't that bad, though, is it? This is pretty straightforward. Everybody good? Okay, all right. I do want to introduce the next deflection method that we're going to do, which is pretty simple. There's really not a whole lot to say about it. And it's the method of superposition, okay? Now, what I mean by the method of superposition is this, okay? For the purposes of what you're doing in here, you really only need a basic understanding of beam deflection. If you want to get a real, significant understanding of beam deflection, take structural analysis, because that's one of the big topics in the class, am I right? And we do, in there, we learn a method where you can calculate the deflection of any beam due to any load anywhere, okay? And it's a little space-agey when you think about the derivation, but it all goes into energy methods, law of conservation of energy. You physics folks are really excited about that. What I'm more interested in your ability for the purposes of this class to do is superposition, okay? And what I mean by that is some of the more basic cases of beam deflection are derived, okay? They're pretty easy to derive. And let's say we have something like this. Well, I have a beam that's subjected to a uniformly distributed load and then a point load at midspan. Well, the distributed load, we just did that, right? We just derived that equation. So I'm assuming you all know how to derive that. The same thing is true for the other, okay? I propose that like if I was trying to define or determine the deflection, let's say right here, due to these loads, I propose that we could say, well, let's find the deflection due to the distributed load. Let's find the deflection due to the point load, And let's just add them up, right? That's the method of superposition, just taking each case one at a time and then just adding those results, sort of superimposing the results together. Does that make sense? Now, in order to do that, you need beam deflection formulas, which I gave you a handout on that, I believe, that last time when I handed out everything. Okay? So if you don't have it, no big deal. You should have your textbook, right? You should bring that with you every day. But, oh goodness. No big deal. I did give you this. So this is deflections and slopes of beams. So there's a whole host of different different formulas and scenarios. So this is deflections and slopes of cantilevered beams. Now you can see they define their coordinate axes a little differently. They said the coordinate axis starts at the fixed end as opposed to the free end. Personally, I think it's a little easier to do the opposite, but that's just me. Okay, more cantilevered beams. See this one, if we had done this one symbolically, we would have gotten these answers. But if you want, you could plug in PL cubed over 3EI for the beam that we just derived using those units, and you'll get the same answer. So just something to keep in mind. What I'm more interested in, or at least showing you right now, is this one. Deflections and slopes of simple beams, so stuff like this. Now, look at this. A beam simply supported, uniformly distributed load. Look at that delta max. 5WL to the 4th over 384 EI. It's funny how we derived that one, right? All right, you look at this deflection formula, this one right here, Q over 24 EI. You look at this, that is the same thing that we derived. All they did was factor out some like terms. That's it, okay? So what's that? V, they're saying V is deflection. That's what they're saying. I'm not a fan of that, but it is what it is. If you look here at the top, you have here, so V is the deflection, V prime is the slope. Delta C is the deflection at midspan. They also have a delta max, and then they have rotations at either end. Okay, so if I look at this case, for instance, V is the deflection anywhere along the beam. V prime is the slope anywhere along the beam. This is the deflection at midspan, and these are the rotations at either end. Again, they're the same thing. We used W for our load. They're using Q, but it doesn't matter. In the end, we're getting the same thing. Make sense? Four. Voltage.
Oh no, thermo is the best because you've got V and then you've got the weird like Latin V that you can't
Well,
actually write.
Well, Poisson's ratio though. That's the.
That would make math a lot easier because you could just combine all the V's.
That's it. The answer is V times however many V's there are. We'll knock this problem out really quickly next time. Well, actually, you know what? We might be able to do it right now, actually. Oh. Actually, you know what? I am. Let's go ahead and do this right now because this is a really quick problem. I want to determine the deflection in a beam that's L over 4 away from point A. So I want to determine a deflection right here. Does that make sense? So we have a simply supported beam subjected to a uniformly distributed load and then subjected to a point load. Okay? So here's how this works. Okay? We go here and we say, all right, here is our beam deflection equation for uniformly distributed loads, right? Pretty straightforward. So all I do is I plug in L over 4, right? X equals L over 4. So there's that one. For the point load at midspan, I scroll down a little further, and I get this one right here. So a similar formula. Okay? So I just plug in X equals L over 4, right? Get a deflection for the first one, get a deflection for the second one, add them up, and that's it. Simple? Everybody okay with this? All right. So, this is simple. So for the distributed load, we have V of x equals minus QX over 24 EI times L cubed minus 2LX squared plus x to the third. Okay? So if I plug in L over 4, and keep in mind I'm dealing with a W, it doesn't really matter, but I guess minus W times L over 4 over 24 EI times the following. Yes? That was what the problem was asking for. The problem was saying, tell me what the deflection right here is. L over 4 away from A. No, that's fine. Sound good? All right. So we do the same thing. L to the third minus 2L times L over 4 squared plus L over 4 cubed. Now, when you go through and do all the grunt work, you're going to get V equals the following. Okay, and I know it seems kind of nasty, but it ends up being 19 WL to the fourth over 2048 EI. And you're like, whoa, that's a fraction. I understand. Here's where that's coming from. Here's where that's coming from. We've got minus WL over 96 EI. And I guess what I should do is indicate that that's downward, but that really doesn't matter. I'll just do that. But you're going to end up having L to the third minus L to the third over 8 plus L to the third over 64. Everybody see that? So you take 1 minus an 8 plus a 64th and then multiply it by 96. Your calculator can handle that. What's that? That's fine. I mean, there's nothing wrong with that. Okay? Now, for the point load, V of x from that table is minus px over 48 EI for x squared. So at L over 4 minus P L over 4 over 48 over EI, 3L squared minus 4 L over 4 squared, and you get V is 11 PL cubed over 768 EI down. So I propose that if you want to find the deflection due to both of those, I'll say V total and there you go. I know the formula looks nasty, but in the end, it's just plug and chug and multiply your whole result times 1728. That's it. There's really not much else to say. Does anybody have any questions on this? All right, let's talk a little bit about the plan. So I decided, since you all just had are still getting over your celebration, instead of giving you a homework on this today, I decided to be nice and give you a homework on Tuesday on beam deflection. Now, just so everybody's aware, on Tuesday again, we're going to have Dr. Nichols come and visit us for a little bit, so you know, it's just routine and whatnot, so he's just going to be hanging out in the back. Try and be here on time and whatnot. Next time, what we're going to do is discuss stress analysis. And the reason why that's important is we've looked at, well, how do you handle something being yanked on, something being twisted, something being bent, something being sheared? Well, what if you have multiple of those instances all going on at the same time? So we have to determine how to analyze for stress. And really our starting point is trig. So we got to do some trig. So be prepared for next time for there to be some trig, okay? The unit circle and identities, and you're getting on to some. You're getting close to something right there, because we use a technique called Moore's circle, and it's funny how there's some striking similarities there. So that's all I got. You all have a good weekend. We'll see you next week. The sign-in sheets are around, so if you haven't signed it, go ahead and sign in.